Electricity can be generated by various systems, such as an old-fashioned water wheel. Unfortunately, wood is severely subject to degradation, rot. But would it have been better if it was made from metal? Everybody have had or seen a tool, bike or whatever from iron metal that starts to rust. This iron reacts with oxygen from the air to form iron oxide, rust, usually observed as reddish-brown layer on top of the surface. This reaction of the iron, also called oxidation, is accompanied by the loss of energy, liberated as heat. Although we don't really perceive this heat, it does exist, and it would be great to put this energy to good use so as to convert it into electricity. We then are talking about an electrochemical cell or a battery, where it is possible to allow the reactions to take place in a controlled manner, making sure we can use the electrons that are donated by the iron. Iron is not the only metal that can react to deliver electrons. The lithium-ion battery can do that too. In the new sodium-ion battery also. But the well-known lead-acid battery has a metal that is doing this job. It seems that particularly metals and metal ions are important components for the storage of electrons. Actually, metal ions can be used in, for instance, redox flow batteries, where the components are stored in big tanks, rather than in small cells. How these basic systems work, we will see, starting with the lead at the battery. The name itself explains a lot. It is a battery based on lead and lead oxide at both electrodes, separated by an acid, sulfuric acid, the electrolyte. This battery usually comes in a plastic box that contains 6 units, the cells, where the electrochemical reactions take place. Each cell will provide 2 volt, giving the well-known 12-volt lead-acid battery. Sulfuric acid itself is essential as it reacts with the lead as well as with the lead oxide to form at both sides lead sulfate. It means during using the battery, sulfuric acid is being consumed, and this is governed by a drop in the viscosity of the liquid electrolyte. In previous times, in a garage, the mechanic measured the viscosity of the liquid to verify the state of charge and whether the battery is dead or not. These days we do it differently, also because the current batteries are not allowed to be opened, such as the lithium-ion battery. Despite the metal lithium essentially acting similar to lead, the process is significantly different. Here lithium ions shuttling back and forth between the electrodes and do not stay at the electrodes. That is why it's called a lithium-ion battery. The interesting thing is that these lithium ions are being inserted in the electrode materials, as these were sponges. This prevents the systems to change too much during successfully charging and discharging. At the positive electrode, a metal ion is available such as nickel, manganese, cobalt that allows to accept the electrons from the lithium on discharging and vice versa on charging. The negative electrode today is usually a carbonaceous material, similar to graphite. The positive and negative electrodes are separated by a porous plastic membrane that could be regarded as a filter paper in which the liquid electrolyte has been dispersed. There are various types of lithium batteries, which are usually referred to the positive electrode material. NMC stands for nickel, manganese, cobalt, and we see often NMC 622 or NMC 811, which reflects the ratio of the nickel, manganese and cobalt. Another lithium-ion battery is referred to as LFP. In this LFP battery, the positive electrode consists of lithium iron phosphate, where the iron ion accepts and donates the electrons. On the negative electrode, research is carried out to replace graphite with silicon, since silicon can host way more lithium than graphite and so increasing the energy density. Many more combinations are possible and research in this field is still going on. Also other systems are under study, such as redox flow systems. The most mature redox flow system is operating with lithium ions at both electrodes. The active ions are dissolved in acidified water and are stored in tanks. The liquid is then pumped through a reactor where acidic ions are exchanged to compensate for the electrons that are transferred from one vanadium ion to the other in the opposite electrode tank. Since these tanks are quite big and the liquid is being pumped, the system is only suitable for static electricity storage in, for instance, grid storage applications. After showing the various battery systems, we can summarize the batteries with respect to their potential applications, which can be seen in this table. We can distribute the different batteries over the various applications. Medical implants will use lithium-ion batteries or more expensive systems not showed here. For consumer electronics, lithium-ion batteries are the best choice. For transport, lead-acid will still be strong due to price as starting, lighting and ignition battery. But for electric vehicles, lithium-ion batteries are selected. Once it comes down to grid connection or large-scale electricity storage, lead-acid, lithium-ion and redox flow batteries can be used. This depends still on the size of the grid, the price we are willing to pay for it, and what we accept with respect to safety and recycling.